Hello everyone. Today I will be presenting my project on my COVID social distancing simulation. Firstly, I'd like to explain the goals I had in mind when creating this project. The main goal was to create an agent-based simulation of COVID-19 with respect to social distancing and how infection can spread without proper following of the rules. The simulation would have emphasis on accuracy and flexibility. Flexibility would be achieved through many variables that can be manipulated, whilst accuracy would be achieved by statistically relevant data that would affect factors such as increased chances of infection when not wearing masks. The most obvious reason why this project is relevant is the still ongoing spread of coronavirus. Even though vaccines have started to be given out, we're not out of the woods yet, as infection is still a real threat with real implications. Hopefully, the simulation will help show how not taking social distancing rules seriously could result in more damage than one might think. Another reason for why this project is important is because it could help give us insight into the most and least important factors to stopping the spread of coronavirus. In order to show how the simulation works, I will firstly describe the classes and their roles. Then I will show how they interact with each other on a small scale. Firstly, we have the person class. Each person has a unique ID number, chance to be infected, set at nearby places, chance to leave their house, a certain level of extroversion, and such. Most of these variables are affected by changeable factors, such as percent of people who wear masks, which potentially affects the chance to be infected. Then we have the place class, which each person may or may not be near. Places resemble a public area, such as a grocery store or restaurants. Finally, we have the house class, each house holding a certain amount of people. In this small scale example, we have 2 houses, each with 4 people. These 8 people are all near a place, and therefore might potentially visit it. Here, one person from each house has decided to visit the place. So has another individual from a different house nearby, off-screen. This individual is infected and can be seen interacting with one of the uninfected people. This person got infected, most likely due to large chance of infection caused by lack of rule following, or maybe he was just unlucky. When this person heads back home, he infects a few of his family members. This process is one iteration, or a day in the simulation. That's how the simulation runs with a small scale example, but due to scalability, it can run many different people, places, and houses. Different people can be near different and similar places. As the scale grows, this creates a network of possible infection spread, similar to real life. As mentioned previously, one of the main objectives I had was to have a flexible program. This was done with many changeable variables that all affect the simulation differently. Some of these variables include the number of people, houses, and places, the average willingness to exchange with someone else in the same place as you, percentage of people who wear masks, percentage of people who stay 6 feet away, and more. For the tools, I only used a minimum amount. Due to time constraints, I wasn't able to add an effective user interface, other than plotting a graph using Matplotlib. For the programming, I just used Python. Now I will demonstrate how the simulation is used. So here we have our code, and right here is our global variables that we can manipulate to get different results. Right now I have something somewhat realistic set up, where 95% of people wear masks, 95% of people stay 6 feet away from each other. The average extroversion, so the chances someone is going to approach someone at a place, is about 5%. The starting infected is about 10% of the population. There's 300 people, and then there are 5 people per house, and then the number of places is 30, and the places per person is 2. And then the number of houses is just the number of people divided by people per house. So if we run this, we can see it's pretty linear. Whenever the infection starts at 10% on the first day, right here, you can see about a 8% increase after 10 days. Now that's a bit drastic because there's not many situations where 10% of the population is infected. But if we say we change these variables to only 10% of the people wear masks, 10% of the people stay 6 feet away from each other, and everyone is super extroverted, so everyone's going to want to approach each other, and no one's following the rules, basically. And the population is still starting at 10% infected, we will get after 10 days, we'll get almost pretty much 100% of the population is infected. For my future plans, I first of all plan on implementing a hill climbing algorithm that manipulates variables in order to find the best ratios that maximize freedom whilst minimizing infection rates. I'd planned to do this from the beginning, but unfortunately, due to time constraints, I couldn't implement it. This also goes for the user interface, as right now it's just a boring graph, and in order to change the variables, you need to go into the code to do so. The last thing I plan on doing is adding more variables that make the simulation more accurate. That concludes my presentation. Thank you for listening.